this is, right, purpose, procedure, pre-lab questions were down here at the bottom. And then your data and observations should be filled in. So you guys did pretty much all of the pre-lab Thursday, collected some of the data and observations, and then your lab partner should have given you the other data and observations. So after purpose, procedure, pre-lab questions, and you're in the lab and you collect data and observations, we move on to post-lab. Now, I used all 50 pages in this, so I have to move to a new lab notebook. But if you have space at the bottom or you did the pre-lab questions on a new page, you're just going to continue on. And the next section that we're going to do is calculations. So when it comes to calculations, we always want to make sure that we're showing work. So it might be showing a quick conversion. Yeah.
If I have room at the bottom, but like probably not enough room to finish all the calculations, just go to the next page.
Oh no, you can start. So if you want to start like a couple calculations and then go to the next page, that's fine.
Okay, perfect.
Yeah.
Thank you.
Yeah, that's what I did. So here, I'll show you what I did with the other class. So let's see, this was your class period. So for example, like first period, I ended up starting it, but then I got like 1 through 6 done. So then I just had to go to the next page. So then at the top, you just want to put calculations continued and then just keep going through. Yep.
Thank you.
Yep. So for calculations, not only do we want to make sure that we're showing our work, but the one thing that people always forget in a lab report, because remember, this is considered your lab report, is labeling the calculations. So on the lab handout, the calculations start down here at the bottom. So I'm going to read the first one. So what's the percent by mass of copper in the post-1982 penny? So for calculation, I'm going to say number 1. And I want to give it a quick label. Now, I don't have to rewrite the whole question. I'm just going to do something like this. Percent mass Cu. I'm just labeling the calculation because what this allows me to do, so when you've turned your lab in, it allows me to, maybe I want to look at one of the calculations for everybody. It's easier for me when they're all labeled to look and say, okay, there's the percent mass of copper. I can look at each person's and then I can move on. Because sometimes I'll check calculations to make sure that you set it up and performed it correctly. So I'm just going to label percent mass of copper. Now, as I work through these calculations with you guys, I am not using sample data. I am going to be writing very generic calculations. I want you to be putting your data in and actually doing the calculations. So for percent mass of copper in a post-1982 penny. So a post-1982 penny is made of copper and zinc. If I want to find the percent by mass of copper in the post-1982 penny, I'm going to take the mass of the copper shell, and I'm going to divide by the mass of the filed penny. And then percent by mass means I multiply it by 100. Because percent by mass is part over whole. So, for example, if I wanted to know what's the percent of boys in this class, count up the number of boys, divide by the total number. All right, or same thing with girls. What's the percent of girls in this class? Count up the number of girls, divide by the total number. Well, it's the same thing for this. So we take the mass of the copper shell. So I'll put grams of Cu over the total mass of the filed penny times 100. So look back at your data. So the mass of the copper shell is what your lab partner collected on Friday. So after the reaction was completed, there was nothing but a very like malleable copper shell. So you're going to take your mass of your copper shell divided by the mass of the penny, the mass of the filed penny. After you guys filed it on Thursday, you found the mass of it. That's what goes on the bottom, times 100. That's going to give us the percent. So again, whether you want to use, like if you have a calculator, you want to use your phone as a calculator, or if you want to just put your numbers in and calculate it later, that's fine too. So that's how we find the percent mass of copper in the penny. It's probably a relatively small number. Most people's copper shells were anywhere from like 0.04 to 0.08 grams divided by the mass of the filed penny, which for most people was something, 2 grams maybe. It's going to be a pretty small percent. Just don't forget to multiply by 100 though to make it a percent. So calculation 2 says use the prices you looked up in the pre-lab to determine the cost of a pre-1982 penny. Assume it's 100% copper. So again, I need to give this a label. So I'll do cost of pre-penny. I don't need to rewrite the whole question. Just a quick, here's what I'm trying to find. So for everyone, I gave the mass of the pre-1982 penny to everyone. That's what's written on the board. So everyone's going to have the same calculation for this. So I can actually do this calculation with you. The mass of the pre-1982 penny was 3.10 grams. And it said that assume that the pre-penny is 100% copper. So we're pretending, or assuming, not pretending, making the assumption, that all 3.1 grams of the pre-penny is copper. And what it wants us to do is use the cost of copper to figure out the cost of one of these pennies. So I gave you the pounds to grams conversion on the lab sheet. There are 454 grams in 1 pound. And the reason that we had to go to pounds, right, even though pounds is an English unit, right, we're the only ones that use pounds, we need to use the grams to pounds conversion because the cost of copper we found per pound. So if I look back at our pre-lab questions, our cost of copper that we found was $2.92 per pound. So that means that for every 1 pound of copper, it costs $2.92. So we'll all have the same calculation, 3.1 times 2.92 divided by 454. 0.0199. Now remember, this is dollars. My unit for this is dollars, so just put a $ sign at the beginning. Now I wanted to keep it out to 3 significant figures because we are going to have to use this in later calculations. But I do want to just make note of what this means. So normally, if we're looking at money, right, 0.01 is 1 cent. Well, if we look at how this rounds, 0.0199 rounds up to 0.02. It rounds up to 2 cents. So essentially, making 1 penny before 1982 cost 2 pennies. Right? So we're actually going to be looking at why they switched. But that just looks at the cost of the pre-penny. So then calculation 3 says calculate the cost of the copper in the post-1982 penny. So cost of CU in post-penny. Now we had to be specific with cost of the copper in the post penny because a post 1982 penny is made of copper and zinc. So just the copper is in the shell. So the copper shell that your lab partner rinsed and dried on Friday, that's the only copper that there is. So I'm going to put mass of shell, but I want you to put your data. So put in your mass of shell, the mass of your copper shell. And then the calculation is going to pretty much look the same. We're going to convert from grams of copper to pounds. And then 1 pound costs $2.92. So again, take your mass of your copper shell, so look back at your data and observations, go from grams to pounds, pounds to dollars. And again, our answer will be in dollars. And you can go out to 3 significant figures, but remember that leading zeros are not significant. So for most people, they find like 0.000 and then numbers after. And most people have really small numbers. You have your mass of your shell, grams to pounds, pounds to dollars. This is the cost of just the copper. If for some reason you didn't get the mass of your copper shell yet, just make a note, massive shell. I'm actually recording this right now, and this will get added to the copper lab in Google Classroom. So if you need to go back and review these calculations, you can. Okay, so calculation number 4. So now we're flipping to the back of the lab handout. Calculation 4 says determine the cost of the zinc in the post-1982 penny. So I'm going to label this cost of zinc in post penny. Remember, you're going to have plenty of space in this lab notebook, so you want to make sure that everything is spaced out, easy to find. Circle or box your answers. Just make it as easy as possible to find. Now, with this, we did not actually find the mass of zinc that reacted, because it reacted out of the inside of the penny. However, we do know the mass of the filed penny. We know the mass of the copper shell. So law of conservation of mass says if we know the mass of the filed penny and we know the mass of the copper shell, how can we find the mass of the zinc? Subtract them. Yep. So I'm going to just make kind of a small note up here. Mass of zinc, and you guys again can actually plug your numbers in, is mass of filed penny minus mass of CU shell. So we can find the mass of zinc that reacted in this penny by taking the mass of the filed penny and subtracting the mass of the copper shell. Again, the law of conservation of mass says mass is neither created nor destroyed. So if you start with a specific mass of a penny that consists of just copper and zinc, and you subtract the mass of the copper, you're left with just zinc. So once you know your mass of zinc, you can actually go through and do this calculation. Now this will look similar to the copper, except the cost is going to be different. There are 454, oh man. So see, I started to write pounds here. So if you mess up, just single line through it. I started to write grams, pounds. So grams of zinc, that's your mass, grams to pounds. And then 1 pound of zinc costs $1.11. Again, this came from the pre-lab. I'm just looking at the pre-lab questions. right down here. I just have it in a different lab notebook because I ran out of pages. So this came from the pre-lab. So again, you can keep it out to 3 significant figures, but your answer here is in dollars. So this is the cost to produce the zinc that's in the penny. So we figured out the cost of the copper in the penny and the cost of zinc in the penny. And then finally, number 5 says, sum up the answers to 3 and 4 to get the cost of materials in a post-1982 penny. So I'm just going to label this cost of post penny. And again, once you run out of space, if you need to go to the next page, you're just going to continue on just like normal. Just remember, blue page and yellow page should be together. And then you'll flip to the next one, and you can just write calculations continued at the top. So the cost of the post penny. We're going to take the cost for the copper, so this is from number 3, plus the cost of the zinc, which is number 4. That's going to give us our cost of a post penny. Right, it still should be 0 point something. Should find that it's less than 1 cent. So it should be less than 0.01. So what we did in number 5 is we used 3 and 4. Right, we added those together. And then the last calculation that deals with money, calculation 6 says determine the savings for the production of 1 million pennies. Okay, so I'll label this savings of 1 million pennies. So essentially this question, we're looking at how much money did the US government save by switching from pure copper pennies to copper-plated zinc pennies. So let's start by looking at the cost to make 1 million pre-1982 pennies. We will all have this same pre-calculation. So it cost us, and by us I mean the United States, $0.0199 to make a penny. So 0.0199 to make 1 penny. Well, let's figure out how much it costs to make 1 million pennies. 1 million is 1 times 10 to the 6th. If you want to do 1, 6 zeros after, that's fine. But let me show you what this looks like. So 0.0199 times. Now, if you use a calculator like mine, there is this EE button right here. So it's if you hit second, x to the minus 1, that stands for times 10 to the power. So for 1 million, I just do 1 E6, and that turns into 1 million. So it's 19,900. That's money. $19,900 to make 1 million pre-1982 pennies. Well, 1 million pennies is actually $10,000. So the government was spending almost double to make pennies out of all copper. Now let's look at the cost to make 1 million post pennies. So you're going to put your cost from number 5, and you're going to multiply it by 1 million. So again, everybody's answer is different here. But take your cost from number 5, multiply it by 1 million, That's how much it costs the government to make 1,000,000 pennies after 1982. It should be less than 19,900. So this is how much it cost before. This is how much it cost after. If we subtract them, that gives us the amount of money that the government saved. So we take 19,900 and we subtract the amount that it costs to make 1,000,000 post 1982 pennies. And that will give us our savings. Any questions on 1 through 6? You guys that are online, any questions on 1 through 6? If you guys have any questions, you can type them. I can hear the chat pop up. Okay, so then we will move on to calculation number 7. Now we're getting into like the actual stoic. So now we'll get into grams to moles, things like that. Label this period 6. So now I'm not done with my calculations, but I had to move on to the next page. So this is what it's going to look like. I'm going to do calculations, and I'm just going to do CTD for continued. You want to write out continued, that's fine. But you always want to label every section. Just make it easy to follow, easy to read. So calculation 7 says calculate the moles of zinc that reacted. All right, so moles Zn reacted. Now, if we actually look back, calculation number 4, you actually found the mass of zinc that reacted. Right, so this grams of Zn from number 4, that's what we want to start with in number 7. So if you look back at number 4, when you did massive filed penny minus massive CU shell, that gave you grams of zinc. That's what we want to start with here. So we have grams of zinc. Again, this is different for everyone, which is why I haven't been putting numbers in to start. I want to go from grams of zinc to moles of zinc. How do I go from grams to moles? What gets plugged in here? Or where do I find this mass? All right, smaller mass in the periodic table. So, where's my yellow here? Oh, there it is. All right, so yellow periodic table. All right, you guys picked this up last week. This is what you get on everything. Here's zinc, 65.38. Now, if you're like, oh, I don't know where this periodic table is. Well, here's a fun fact. There's a periodic table right here, too. So you can just flip the page over and look at the periodic table. So when you take your grams of zinc and you divide by the molar mass, that gives us our moles of zinc that reacted. And again, 3 sig figs is fine. And so 3 significant figures should be okay. Number 8. Let me flip this around. So number 8 says using your balanced equation from the pre-lab. Right, so that gives us a hint as to where we should be looking. Determine the volume of hydrogen released. So let's label this calculation volume H2 released. Now, I don't really have much information to go off of in terms of my given information. So let's use what we just found. Let's use moles of zinc because we know how much zinc reacted. And if we look at the pre-lab, we only have a certain number of reactants. We have zinc or HCl. We haven't really done anything with HCl yet. So let's use moles of Zn to start this calculation. Now it said use the balanced equation from the pre-lab. Here was the balanced equation that we did in the pre-lab. We did Zn plus 2HCl yields H2 plus ZnCl2. So right now we're focusing on zinc and hydrogen. So it's a 1-to-1 ratio. Remember, when you do any stoich, if you want to go from one substance to another, it has to be in moles, because the balanced equation tells you the mole ratio. So we just said for 1 mole of zinc, we produce 1 mole of H2. So that lets us cancel out moles. Now we're at moles of H2. Now up here, right above me, I have this beach ball hanging. It says 1 mole equals 22.4 liters. That's molar volume. I have lots of fun things around the room that actually help you out. Molar volume is one of them. Now we can only use molar volume at STP, which is why it says assume STP, standard temperature and pressure. So when we are at standard temperature and pressure, 1 mole of a gas, so in this case 1 mole of hydrogen, occupies 22.4 liters of space. And so we can take our moles of zinc, so whatever your number of moles of zinc, you calculate it in number 7, and multiply by 22.4. That gives us our volume of hydrogen. So when you put that penny into that hydrochloric acid and you saw the bubbling, you produced hydrogen gas. This tells you exactly how much hydrogen gas you produced. So if you would have collected the gas, this is the volume of gas that it would occupy. So again, that's using the idea that 1 mole of a gas occupies 22.4 liters of space at STP. Nice stoich review. Where do we get the grams of? Oh, so grams of zinc is from number 4. So grams of zinc in number 7 that we started with. Came from number 4 when you took the mass of the filed penny minus the mass of the copper shell. So whatever grams of zinc you started with in number 4 is the grams of zinc you're starting with in number 7. So from number 4. Okay. Any other questions on 7 or 8? Where we got any numbers from? Okay. Noah, did that answer your question? Welcome. Okay. So then calculation number 9. Calculate the molecules of hydrogen given off. Okay. Molecules of H2. When it comes to starting with an amount, there are 2 ways that you could do this. I'm going to show you one of the ways, I guess. I'm going to start with moles of zinc again. So down here, I'm going to start with moles of zinc. You could start with liters of hydrogen and you could work backwards that way. I'm just going to do moles of zinc because it's going to have us practice with the stoich. So my given information is moles of zinc. Since it's already in moles, I'm good to go in terms of starting. Now I don't want zinc. I want hydrogen. So to convert from one substance to another, I'm going to go from zinc to H2, mole ratio. Same mole ratio as number 8. It's coming from the same balanced equation. It's 1 to 1. Now, instead of using what we did up here with molar volume, it now wants molecules. So this box stays up on top of that cabinet all year long, unless keystones are given in here and then I have to take down. Any other time it stays in here. But this box, this side is always facing you. So 1 mole of anything is 6.022 times 10 to the 23rd molecules or particles or formula units or anything, right? It could be you want 1 mole of donuts. So it's 6.022 times 10 to the 23rd donuts, right? 1 mole is always Avogadro's number of something. So what we'll do is say 1 mole of H2, 6.022 times 10 to the 23rd molecules of H2. Now notice how my shortening, my abbreviations are a little bit different from moles and molecules. I don't ever want to write out molecules completely, but I need to make sure I can tell the difference between moles. So I use MOL for mole, MOLEC for molecules. If you have a different way of abbreviating molecules, that's fine, but just make sure you tell the difference between moles and molecules. So if I double check, my moles of zinc cancel, moles of H2 cancel, I'm left with molecules of H2. And so put this in your calculator. This is why a scientific calculator is important, because you have to be able to put Avogadro's number in. So that means on ones like mine, I would do whatever my moles of zinc is times 6.022 E23. And then I would hit enter. Now, keep in mind, right, this, I'm making up a number, don't use this at all. 0.05 times 6.022 E23. Right, so if I get an answer that's 3.011 times 10 to the 22nd, please remember that anything before times 10 is all you count with significant figures. So Avogadro's number, for example, 6.022, that's 4 significant figures. So when you're rounding, just keep that in mind. So you take your moles of zinc, multiply by Avogadro's number. Don't forget the times 10 to the whatever either. Always look off to the side, right? Because calculators like mine, you have this little times 10 to the something off to the side. Okay, so that's calculation number 9. So calculation 10 tells us that the zinc present was a limiting reactant. So now we're dealing with limiting reactants. All right, so zinc was limiting. Zinc is what determined how fast our reaction went, when our reaction stopped. Because zinc was limiting, once the zinc was used up from inside the penny, the reaction was over. So we didn't have any more zinc to be used. And so then it said HCl was in excess. Using your balanced equation, how many moles of HCl were actually needed? Keep in mind when you are looking at significant figures. So unless it specifically says pay attention to sig figs, if you give 3 sig figs, you're okay. When you're looking at significant figures, though, you should always be looking at your given information to determine your number of significant figures. Any conversions that we use, molar volume, Avogadro's number, those are actually considered in like infinite sig figs because they're exact numbers. And so you don't ever use the conversions as sig figs. So you always want to use your given information to determine your significant figures. But if you do 3 sig figs, you should be okay. So number 10. So zinc is limiting. HCl is in excess. That's why it didn't actually matter how much HCl you poured into the beaker, because as long as you had 20 milliliters, HCl was in excess. If we really cared about how much HCl was being added, if that was going to be part of our calculations, I would have had you measure out the HCl using a graduated cylinder. Because graduated cylinder is much more precise than a beaker with 4 lines on it. But because it was in excess, it didn't actually matter for us. So we want to figure out how many moles of HCl are actually needed. When you have a limiting reactant, that limiting reactant drives all calculations. So once you know that a limiting reactant exists, that's what you have to use for every single calculation. So I'm going to start with my moles of zinc, right? Because that's my limiting reactant. I don't want zinc, I want HCl. So I want to go from zinc to HCl. When you want to go from one substance to another, you have to use the mole ratio. And this mole ratio always comes from a balanced equation. So again, if we look at our balanced equation, it's 1 mole of zinc to 2 moles of HCl. So 1 mole of zinc to 2 moles of HCl. And then that's it. Because moles of zinc cancels, we're left with moles of HCl. So you can take your moles of zinc and multiply by 2. So again, this was the amount of HCl that was actually needed. So in order to react with all of the zinc that was in the penny, this is how many moles of HCl were required. Now number 11 says, if you used 20 milliliters of 6 molar HCl, how many moles of HCl did you actually use? So when we poured 20 milliliters of 6 molar HCl into the beaker, how many moles of HCl were we actually pouring into the beaker? That's what this question is asking. So we'll label this moles of HCl used. And so it says, recall that molarity is moles of solute over liters of solution. Moles of solute over liters of solution. So molarity, another word for concentration. Moles of solute over liters of solution. SOLN is how I abbreviate solution many times. Like you'll see me abbreviate RXN for reaction. So we know that we had 6.0 molar HCl. Every acid, whether it's a strong acid or a weak acid, is an aqueous solution. For me to prepare an acid for lab, I have to take concentrated acid and dilute it down with water. So it's a solution. I want to figure out how many moles of HCl, that's my solute, we have. But now here's the big thing. This is very commonly missed at the beginning of the year until I drill it in everybody's minds. It's liters on the bottom. I don't care what you measured in the lab. To plug it into the molarity equation, it has to be in liters. Now I'm going to do the conversion down here. You don't have to show this conversion. If you want to just move the decimal over, that's fine. How many milliliters are in a liter? 1,000 milliliters in a liter. If you remember any metric conversion, it should be this one. This is the one we're going to use the most. 1,000 milliliters in 1 liter, which is why you could go 1, 2, 3, and move the decimal. So that is our liters of solution. Has to be in liters to plug it into the molarity equation. So we're all going to have the same calculation. 6 times 0.02, 0.12 moles of HCl used. Right. Another way, I guess, to think about this is that's how much HCl we had available. That's what was in the beaker. So we poured 20 milliliters of 6 molar HCl into the beaker, and we had 0.12 moles of HCl available for the reaction. So this is how many moles of HCl we had available. this is how many moles of HCl we actually needed to react with all of the zinc. I really hope that your number 10 is a smaller number than your number 11. And then finally, calculation number 12. Using your answers to questions 10 and 11, calculate the mass of excess HCl present. So mass of excess HCl. Now I use like XS to abbreviate excess, like too much. So that's another abbreviation that you'll see me use. So again, here was how many moles of HCl we had available. So 0.12 moles of HCl available. This is what was in the beaker at the beginning. Number 10, we calculated how many moles of HCl we actually needed. So I'm going to put number 10 in my, writing it. You can actually put your number. So number 10 moles HCl needed. So if this is how much I had available in the beaker, but this is how much I needed, how can I figure out how much I have left over after the reaction? What math thing should I do here? Subtract. What's that word? Function. That's the right word. Math function. So 0.12 moles of HCl is what was available in the beaker. Subtract your moles of HCl that you actually needed to react with all of the zinc. That's going to give you moles of HCl in excess. That's how much you had left over. So now, the problem didn't ask for moles, it asked for mass. So I'm going to go right down here. I'm going to take moles of HCl. Right, that's this number right here. I'm taking this number, starting a new calculation with it. I don't want moles. I want to go to grams. You guys have already told me that to go between grams and moles, you need the molar mass from the periodic table. So 1.008 is hydrogen, 35.45 is chlorine, 36.458 is your molar mass. So take your moles of HCl that were in excess, multiply by the molar mass. This will be grams of HCl in excess. So 7 through 12, these calculations helped us to review stoic. Now, in this, it told us exactly what the limiting reactant was. We didn't have to find it. Remember, if you want to find a limiting reactant, if you are given masses or amounts in general of 2 or more reactants, you have to find the limiting reactant first. I know we won't get to a limiting reactant question today, but keep in mind how to find limiting reactants, things like that. Any other questions on calculations?